Recently, we have learned Strassen's algorithm for matrix multiplication in subcubic time. And so, how do we apply this knowledge of ability to multiply matrices quickly in other problems of computer science? Now, this week we'll learn how it helps in some graph algorithms. Usually these algorithms are related to shortest paths, and we will learn two of them. Recall that Strassen's algorithm allows us to multiply matrices in time, which is big O of n to the power of log 27. After Strassen published his result, there was a chain of results, and it still continues. And currently the best known time for matrix multiplication is big O of n to the power of 2.38 roughly. So during the last decade, the improvement was only in the third sign after the decimal point. And currently, this is roughly the best known result that we have. But here we can find parallelism to multiplying integers. And if we are talking about integer multiplication and bit complexity, then our first algorithm that we've learned was Karatsuba and Hoffman. And this algorithm had big O of n to the power of log 23 complexity. Then we have studied Thom's algorithm by Thom, and later it was simplified by Cook, that has complexity big O of n to the power of 1 plus epsilon, where epsilon is constant, but it can be made arbitrarily small. So essentially, we have almost linear time complexity for multiplication of integers. After Thom, the best known algorithm for several decades was algorithm by Schoenhagen Strassen. This algorithm achieved complexity of big O of n log log n. And then there was chain of improvements, and two scientists, Harvey and van der Hoeven, were able to prove that integer multiplication can be carried out in time big O of n log n for n bit integers. So this is the ultimate bit complexity of integer multiplication. Now for matrices, as we see, the progress is much slower, so that we still are unable even to go as close to 2 as possible in terms of power of n, which has been done by Thom and Cook long ago before the latest algorithm in 2019 was devised. And as there currently is no ultimate knowledge for how close to 2 we can get here, and clearly we cannot get closer to n squared here, because just to read the input matrices, we have to read all their elements, and the number of elements is n squared for n by n matrices. So currently there is a nice notation here, which is called the matrix multiplication exponent. So the matrix multiplication exponent is a constant, which we still don't know, such that matrix multiplication has an algorithm running in time big O of n to the power of this exponent plus little o of 1. So this guy is denoted by omega. This has nothing to do with primitive root of unity that we have used to devise fast Fourier transform algorithm, nothing to do with that. But this is a standard letter used for matrix multiplication exponent. Most of the researchers believe that this is actually 2, but currently, to the best of our knowledge, we can just state that omega is less than 2.38. And as we'll learn, improving the matrix multiplication exponent will immediately improve some algorithms that are based on matrix multiplication in many areas of mathematics, including graph theory. So we'll just study application of matrix multiplication currently for solving two problems of graph theory. Let's talk about these problems.